The meeting was yesterday, but we'll reschedule for next week. Read that sentence. Now, try to put it on a calendar. You cannot, unless you know when the sentence was written. Yesterday means one thing on July 11th and something else on July 12th. Next week means one range on Monday and a different range on Sunday. Time expressions in text are almost never absolute. They are anchored to a reference date that lives outside the sentence. This is temporal processing, extracting time expressions from text, normalizing them into standard dates, ordering events in time. It sounds trivial. It is not, and every calendar assistant, contract parser, news analytics dashboard, and medical record system on the planet depends on it. Last video we probed model understanding with entailment. This video we descend from the abstract to the very concrete. Dates, times, durations, vague words like soon. A whole family of expressions humans handle without thinking, and machines have needed 30 years of dedicated engineering to get partway right. Today's puzzle. A time expression in English can be a fully specified date, liking the 15th of March 2024, a relative reference like next Tuesday, a fuzzy duration like in a few weeks, or a fully vague word like soon or eventually. A machine needs one representation that can hold all of them, and it needs to know how they connect. TimeML is the standard, and we'll walk you through it. Today's 3 beats. First, the problem. Why yesterday and soon break machines? Absolute versus relative, precise versus vague, anchors and reference dates. Second, TimeML and TimeX3. The markup standard for time, Jurafsky 2003. And the TempEval shared tasks that push the field forward. Third, SUTime, Chang and Manning 2012, the rule-based normalizer that quietly runs in production everywhere, and why rules still win on this task. Beat 1. Why is this hard? Take a news article. The meeting was yesterday, but we'll reschedule for next week. To resolve yesterday, you need the article's publication date. That is called the reference date. Without it, yesterday is just a word. With it, you can compute an actual calendar date, but you also need to detect that yesterday as a time expression in the first place, which is a tagging problem, and a hard one because English hides time expressions inside every part of speech. It gets worse. What about soon? The company will file soon. Soon is a real word. It carries real meaning. But how do you put it on a calendar? You cannot resolve it to a specific date. The best you can do is bracket it, probably within weeks, definitely not years. Vague expressions live on a spectrum, and any system that pretends they don't will silently drop them or hallucinate a fake date, both bad. And events don't just happen. They happen in relation to other events. She resigned after the merger closed but before the audit began. 3 events, 2 temporal relations. A machine has to build an order even when the actual dates are unknown. That is event ordering, also part of temporal processing, also brutal. Beat 2. TimeML, James Jurafsky and colleagues 2003. A markup standard for annotating events, times, and the relations between them. 3 main tag types. TimeX3 marks time expressions. Event marks event mentions. TLink marks the temporal relation between an event and a time, or between 2 events. Simple in the abstract, extremely detailed in the guidelines. TimeML made temporal annotation reproducible across labs. Then came the TempEval shared tasks. TempEval 1 in 2007, TempEval 2 in 2010, TempEval 3 in 2013, and TempEval 4 in 2015. Each round posed a slightly different flavor of the temporal problem. Detect the time expressions, normalize them, link events to times, order events relative to each other, and provided a shared test set so labs could compare fairly. The community used TempEval the same way vision people used ImageNet. The through line, TimeML plus TempEval, standardized what temporal processing means. Before them, every lab annotated time differently. After them, everyone spoke the same schema. That is what makes a task benchmarkable. And that is why Jurafsky's paper is cited in nearly every temporal NLP publication of the last 20 years. Beat 3. SUTime. Angel Chang and Chris Manning at Stanford 2012. a rule-based time normalizer that shipped inside Stanford Core NLP and is still one of the most reliable normalizers in production. Give it next Tuesdays plus a reference date, and it hands you back an ISO date. Rules, regular expressions, layered context, not glamorous, just correct. 14 years later, it's still shipping. Why do rules still win here? Because dates and times have structure. Formats are well defined. Calendars are unambiguous. When next Tuesdays means the same thing every time, a regex catches it perfectly, and a handwritten rule maps it to the right ISO date every single time. A neural model has to learn all of that from data, and even then, it makes weird mistakes. For structured, formal expressions, rules dominate. For fuzzy stuff, neural helps. Most real systems combine both. Where it all lands. Modern calendar assistants, contract parsers, EHR analytics, and news timeline tools all use some combination of TimeML annotation guidelines, TempEval style evaluation, and SUTime style rule engines, augmented with fine-tuned transformers for the ambiguous edges. Nobody wins a Nobel for temporal processing. Everybody depends on it. The invisible plumbing under every schedule, the meeting feature. 3 takeaways before the quiz. 1. Time expressions come in 4 flavors: absolute, relative, fuzzy, and vague. Relative expressions need a reference date. Vague expressions like soon should be bracketed, never hallucinated. 2. TimeML from Jurafsky 2003 is the annotation standard. TimeX3 event, T-Link, TempEval shared tasks from 2007 to 2015 provided the benchmarks that made the field comparable. 3. SUTime from Chang and Manning 2012 is the rule-based normalizer that still ships in production. Rules dominate on structured dates. Neural helps on fuzzy expressions. Real systems combine both. Quiz 1. Why can't yesterday be resolved to a specific date without extra context? A. Yesterday's is not really a time expression. B. Relative expressions need a reference date. The anchor, yesterday means one date on July 11th and another on July 12th. C. Yesterday's a proper noun. Or D. English doesn't have a formal representation for yesterday. B. The anchor problem. Relative expressions are meaningless without a reference date. In news articles, the reference is the publication date. In emails, it's the send date. In chat, it's message time. Systems that ignore this either fail silently or hallucinate a date. Both are worse than being explicit about the anchor. Quiz 2. What did TimeML contribute? A. A rule engine that ships in Stanford Core NLP. B. A markup standard, TimeX3 for time expressions, Event for events, T-Link for temporal relations, that made annotation reproducible across labs. C. A GPU-optimized inference library. Or D. A crowdsourced corpus of 570,000 pairs. B. Before TimeML, every lab annotated time differently. Jurafsky and colleagues created a shared schema. TimeX3 event, T-Link. That standardization is what enabled the TempEval benchmarks and the 20 years of comparable temporal NLP research that followed. Quiz 3. Why do rule-based systems like SUTime still beat neural models for structured date expressions? A. Nobody has tried a neural model on dates yet. B. Structured expressions have well-defined formats. Regex plus handwritten rules map them to ISO dates deterministically, while neural models still make weird mistakes. C. Rules are faster to train. Or D. SUTime is a neural model in disguise. B. Dates and times are one of the rare parts of language that are actually formal. Next Tuesdays means the exact same thing every time. A regex catches it perfectly. A handwritten rule maps it to ISO deterministically. Neural models have to learn all that, and even then are less reliable. Real systems combine rules for structure with neural for vague expressions. Back to the puzzle. English lets you say yesterday, next Tuesday, in 3 weeks and soon, and it expects the listener to figure out what you mean. A machine has to reconstruct the reference date, apply the right rule, and know when to bracket instead of hallucinate. TimeML gave us the schema. SUTime gave us a working normalizer. Next video, how to compress a whole document into a paragraph. Summarization. Next time, text summarization. How do you crush a 50-page document into 3 sentences without dropping what matters? Extractive versus abstractive. Text rank. Pointer generator networks. BART. The task where LLMs finally shine and the task where they finally hallucinate. Hit subscribe.